Hello and welcome to another Control Systems tutorial with me, Richard Pates. The topic of today's lecture will be that of observability, and the developments that we will see will very much mirror those for reachability and controllability from an earlier lecture. We will begin with the concept of observability, or lack thereof, for particular points within the state space of a state space model. We will see that a point in the state space is unobservable if it does not affect the measurable output in any way whatsoever. We will then move on to the concept of observability of the state space model itself. We will say that a state space model is observable if its state space contains no unobservable points. Along the way, we will develop simple linear algebraic tools for both testing for observability of state space models and unobservability of points within the state space. But what is it that we would like to understand? Well, in engineering practice, it's very common for the dimension of the state space of the model of the system that we wish to control to be far higher than the number of things that we can measure about the system. Take, for example, the problem of designing an automatic cruise control system for a car, that is, a system to automatically regulate the velocity of a vehicle. Even when using highly simplified models of the engine and the dynamics of the car, the dimension of the resulting state space model will still be far higher than the single useful output measurement we can take, namely the velocity of the car. And this is really what the concept of observability is designed to address. If we're given a very small number of measurements about our system, can we still reliably estimate the value of the state of the state space model that describes it at any point in time? To give a simple, if rather naive illustration of this, consider the two slowly emptying water tanks as illustrated on the left here and on the right here. The heights of the water levels in both tanks can be accurately described by a state space model with two states, x1 and x2. x1 just describes the height of the water level in the first tank, and x2 that for the second tank. Now suppose that for whatever reason we can only measure the difference in these two heights, namely this variable y as illustrated in the figure. Is it still possible to accurately estimate the actual water level heights x1 and x2 based on this measurement alone? And so we arrive at our first concept, that of unobservable parts of the state space. Suppose we have a state space model to which we apply no external inputs. That is, the dynamics can be described by just these two simplified equations here, with x start is equal to ax and y is equal to cx. A point xp in the state space is said to be unobservable if, when we initialize our system at that point, that is, we set x of 0, so the value of x at time t is equal to 0, equal to xp, then y of t will be equal to 0 for all future times. That is, if we were to plot the output y on a set of axes like these on the right, y will remain identically equal to 0 for all time. This is really a very strong requirement. As time passes and our point moves through the state space along some trajectory, say something like this if we had a stable system, this requirement means that the value of cx for every single point along this trajectory must be identically equal to 0. To see that this can happen, let's return to our simple water tank example, but additionally assume that both tanks are identical. Remember that we assumed we were only able to measure the differences in the heights of the water levels in both the tanks. That is, we were only able to measure x2 minus x1. Clearly then, if we put the same amount of water into both tanks initially, y of 0 will be equal to 0. Similarly, since both tanks are identical, they will empty at an identical rate, meaning that the water level heights will remain the same for all future times. This means that y of t will be equal to 0 for all future times as well, and hence the point associated with the initial condition, both tanks have an equal amount of water in them, will be unobservable. Fortunately, there's a very easy way to test whether a point is unobservable. Just as with reachability, this is based on a special matrix. This time the matrix is called the Observability Matrix. To construct the Observability Matrix, we need to know the A matrix, which is n by n, and the C matrix from our state space model of the system. We then use these two matrices to form the sequence C, C times A, and so on, until we get to C times A to the power of n minus 1, where n is the dimension, comes from the dimensions of A. We then take the elements in this sequence and slot them into the matrix n, as shown. And this thing here, this is the observability matrix. We can use the observability matrix to test whether a point is unobservable by simply multiplying that point by n. That is, we form the product nxp. If this product yields the 0 vector, the point xp is unobservable. To make sure that this is clear, let's do a couple of quick examples. So first of all, let's assume that our A and C matrices are given by these two matrices here, and we're asked to test whether the point xp with coordinate 1, 1 is unobservable or not. Note that, roughly speaking, this is corresponding to our water tank example. This A matrix here, this is saying that the rate of change of both of our state variables x1 and x2, those are happening at the same rates. And this C matrix here, well, y is equal to cx. And for this particular C matrix, we see that this is equal to minus x1 plus x2, or x2 minus x1, which is exactly what we saw before. To apply our unobservability test, we need to build the observability matrix. And to build the observability matrix, we need to form the sequence C, followed by CA, and so on until we reach A to the n minus 1. In this case, A is a 2 by 2 matrix, so n is equal to 2, so actually we only need to form these two terms. Well, the first term is very simple, that's just C, so we can just copy that. So C is equal to minus 1, 1. And to get the second term, we need to form the matrix product CA. That is, we need to form the product of minus 1, 1 with the A matrix, which is just minus 1, 0, 0, minus 1. So let's do that. So what does this equal? Well, to get the first term, that's minus 1 times minus 1, so 1 plus 0. So we get 1. And to get the second term, well, minus 1 times 0 plus 1 times minus 1, so that's minus 1. So this matrix here, this is CA, and then we take the elements in this sequence and we slot them into a big matrix, as shown. So first of all, we slot in C, so that's minus 1, 1, and then we slot in CA and we put that here, and so that's 1, minus 1, and that's everything. So this thing here, this is our observability matrix N. Now, to test whether the point xp is unobservable or not, we just need to find the product nxp. So we need to multiply xp, which is equal to 1, 1, by the matrix that we found. So let's just do that. So what does this give us? Well, minus 1 times 1 plus 1 times 1. So that's 0. And 1 times 1 plus minus 1 times 1. So that's also 0. So the product nxp is equal to the vector 0, 0. And therefore this point xp is unobservable. At the risk of doing the unforgivably obvious, let's do a very closely related example. So let's keep the A and C matrices the same as last time, but just test a different point. So let's test the point with coordinate 1, 0 instead. So in the water tank example, we'd have tank X1 with water height 1 and tank 2 with water height 0. Since the A and C matrices are the same, the observability matrix will be the same. So when we do our test, which involves the product nxp, we use the same matrix n. So last time we found that that was equal to -1, 1, 1, -1. And this time we have to multiply it by the point 1, 0. So what do we get? Well, -1 times 1 is -1 plus 0, so -1. And then here we get 1. So with this xp, the product nxp is not equal to 0, 0, and therefore the point xp with this coordinate is not unobservable. Now that we know how to test whether individual points in the state space are unobservable, we're ready for our second concept, that of observability of the state space model itself. In particular, we say that a state space model is observable if no point within the state space is unobservable. So, what does that mean? Well, if we imagine that this set of axes here are describing the state space of our state space model, that means that if we initialize the system so that the state is equal to this point at time t equals to 0, then the output y of t will not be equal to 0. And the same will be true for this point, and this point, and this point, and all of the initial condition points within this picture. So how can we possibly perform our unobservability test for every single point within the state space? Well, just as with controllability, if we're a bit smarter and have a better understanding of matrix vector multiplication, we can avoid this. In fact, the insight that we need is exactly the same as in the controllability case, namely that the multiplication of a matrix n by a vector v can be understood simply as a weighted sum of a set of vectors. In particular, if we associate every column in the matrix n with a vector, as shown here, so the vectors are n1 through np, then the product nv is simply given by v1 multiplied by the vector n1 plus v2 times n2, and so on until we get up to vp times the vector np. So how does this help? Well, what this equation is really telling us is that multiplying by the matrix n is naturally associated with a set of vectors. For simplicity, let's assume that all the vectors are two-dimensional and that p is also equal to, so that we can easily draw things on a set of axes. So if this is our set of axes here, let's assume that this is n1 and this is n2. What this equation is telling us is that when we form the matrix product, what we do is we first rescale the vectors n1 and n2, so we get something that lies along these two lines, and then we just add them together. So if for simplicity we assume that v is equal to 1 minus 1, then we would take n1 and we would subtract n2. So we would subtract this vector here, and the matrix product would give us this vector here as its output. The key thing to observe from this picture is that because the two underlying vectors n1 and n2 were pointing in unique directions, unless v was exactly equal to 0, we would always get a new vector that is somewhere away from the origin. So no matter what point we take along this line here, when we add a new point, no matter what it is along this line here, we'll always get something that's non-zero. And therefore, we would never be able to find a point in our state space, except for the origin, such that nv is equal to 0, and therefore our system would be observable. This concept of vectors pointing in unique directions is typically referred to as independence. In the type of examples that we'll encounter, the concept will always be rather obvious. We'll always be dealing with two-dimensional vectors, and so the idea of independence is simply that they're pointing in different directions, like shown in this picture here. In higher dimensions, it simply means that we're not able to write n1 as a linear combination of n2 through np, and the same for n2 and so on. This can be systematically tested for using procedures such as the Gram-Schmidt process. Do look it up if you're interested. However, for now, let's focus on making sure that we really understand how to perform the test for observability of a state space model. So for simplicity, let's return to the system with A and C matrices that we encountered before. So A and C matrices given as shown here. In fact, we know that this state space model will be unobservable since we already computed that the point with coordinate 1, 1. We already found that this point was unobservable. But let's just try to understand this in terms of our new geometrical insight. So the first thing we need to do is form the observability matrix, but we did that before, so we can just reuse our computation from before, where we found that n was given by the matrix -1, 1, 1, -1. And so we're required to test that the matrix product nv, so this matrix here, multiplied by the vector v1, v2, we need to make sure that for any non-zero vector here, so any non-zero values of v1, v2, that the product nv is not equal to 0. So let's rewrite this as a weighted sum of the vectors associated with the columns of n. So let's rewrite this, and we get v1 multiplied by the vector associated with the first column, so that's -1, 1, -1, 1, plus v2, and this time multiplied by the vector 1, -1. And let's just draw what's going on a picture. So let's just draw the two underlying vectors, n1 and n2, on this set of axes here. Well, n1, that's the vector -1, 1. So that is n1. And n2 is the vector 1, -1. So 1, -1. This is n2. And now we see the issue. Both vectors are pointing along the same line, and therefore they're not pointing in unique directions. This means that we can find values of our input, so values of v1 and v2, such that the product nv will be equal to 0. And this just gives us one simple example. So 1 lot of n1 plus 1 lot of n2 is equal to 0. But there was nothing special about 1, 1. We could have used any point with coordinate c, c, for example, where c is just any number. So any point with coordinates like this will be unobservable, and therefore the system will be unobservable also. And this matches our intuition about the water tank. As long as we fill both tanks up so that they initially have the same water height, so both of the water heights initially are the same, then even as they empty, both heights will remain the same, and therefore our output will be identically equal to 0. Now let's do a very similar example where everything's exactly the same except that we've slightly modified the 1, 1 entry of the matrix A. So in terms of our water tank example, what this means now is that the first tank is emptying at a slightly different rate than the second one, unless alpha happens to be equal to 1. And now let's ask the question, is this system observable or not? So to test for that, the first thing we need to do is form the observability matrix. And to do that, we need to form the sequence C, followed by CA, and so on. In fact, since A is 2 by 2, we know we need to go up to the power of A is equal to n minus 1, so we only need to find these two terms in this case. So let's do that first. Well, C is very easy. We can just copy that down. So C is equal to minus 1, 1. And then CA, we need to form the product minus 1, 1 multiplied by the matrix A. So that's minus alpha 0, 0, minus 1. So that's the matrix A. Let's form this matrix product. Well, the first term is minus 1 times minus alpha plus 0, so alpha. And the second one is just minus 1, like that. So we found these two terms, and now we need to slot them into the larger observability matrix. So the first row is given by C, so that's minus 1, 1. And the second row is given by CA, so alpha minus 1, so we slot that in here. And so that's everything, and that is our observability matrix N. And now to test for observability, we need to form the matrix product NV. So let's write in the vector v here, and we need to make sure that this is never equal to 0 for all non-zero v. So let's rewrite this as our sum of vectors associated with the matrix n. And so we get v1 multiplied by the first column, so that's minus 1 alpha, plus v2 multiplied by the second column. And this gives us the two vectors that are associated with multiplying by the matrix n. And let's just sketch them on a set of axes. So n2 is actually exactly the same. So that's the vector 1 minus 1. So this is the vector n2. But our vector n1 has changed. Now we've got an alpha in this position. So let's just mark a generic point alpha on and see what we get. So the vector n1 is minus 1 alpha. So it's given by this vector here. So now we see that picking different values of v1 and v2 just corresponds to scaling and shrinking these two vectors. And now, oh, that's terrible. That should be going through there. But the point is still the same. Since both of the underlying vectors n1 and n2 are pointing in unique directions, no matter what we choose for v1 and v2, we can never arrive on the origin. So we pick some point along this line associated with n2, we add some point associated with the vector n1, and we'll always end up somewhere away from the origin. And therefore, this system will be observable for any alpha that's not equal to 1. To sum up, today we learned about two concepts. The first concerned unobservable points within the state space of a state space model. A point was said to be unobservable if, when we initialize the state space model at that point, that is, we set the value of the state equal to xp at time t is equal to 0, and we then applied no external input u, the value of the measured output y remained identically equal to 0 for all future times. The set of unobservable points formed an unobservable subspace of the model. That's a set of points for which we could see no trace of them in the output y at all. We then moved on to the concept of observability of the state space model itself. The state space model was said to be observable if its state space contained no unobservable points. We developed effective tests for these based on the observability matrix. Assuming that the matrix here, A, is n by n, this matrix was formed by first producing the sequence C, followed by CA, and so on, until we get to the matrix C multiplied by A to the power of n minus 1. We then slotted these submatrices into a bigger matrix as shown here, and this bigger matrix was called the observability matrix. A point xp in the state space was unobservable if and only if n times xp was equal to 0. We use this fact to show that the state space model was observable if and only if the vectors associated with the columns of this matrix all pointed in independent directions. In fancy language, this is sometimes referred to as the condition that the rank of the observability matrix is equal to n. And that's it for today. Thank you for sticking with it. Next time, we'll try to do something practical with this insight and develop a state observer.